Hi, I'm Jack Buffington for RobotBrigade.com. This is another video in my series of videos about a mapping robot that I'm working on. And in this video, I'm going to talk about my code for the velocity control of the motors. This code is meant to run on the Parallax propeller microcontroller, and I have written it in the propeller assembly language. I did it because I needed the speed that comes with writing in assembly. So let's just jump right into it. The first thing that is important is that you have these variables in your hub RAM, and when you start this core, you pass the address of acceleration to this code. It's very important that these are in this order and there are no other variables within the mix, and that is because since you can only pass one address, you need to calculate the addresses of all these other variables. So that's the first thing that I'm doing. I'm taking the address that is passed and I'm using it to compute the addresses of other variables that I need by this core. Then I'm setting some initial values to 0, and now I'm reading the PID terms. So this is a proportional integral differential position controller at a lower level, even though I'm calling it a velocity controller. That is a higher level of what's running here. Then I'm also reading the acceleration, and we're doing we're starting the loop at this point here. This loop is made to run 1024 times per second, as defined way down here at the bottom of the program, right here. 80 megahertz is the clock rate of the microcontroller, and then I'm dividing by 1024. I keep losing, where is it? Okay, here. Okay. So now I request both velocities that I need, and then I'm going to skip down to a different part of the code before I talk about acceleration. Now we get down here to this bit of code. I have this, and these represent the bits that adjust the position of the two motors. Let me walk you through what's going on. So I have an accumulator that each time this loop runs, I'm adding in the velocity to that accumulator. Now I make a copy of that accumulator, and then I clear away everything but the lower 10 bits in the accumulator. With the copy, I'm shifting it right by 10 bits. And what is left over, what rolled over from the accumulator, is what I should add into my velocity, or into my position, to achieve the velocity that I'm looking for. Since I'm shifting over by 10 bits and I'm doing this 1024 times per second, this works out that over 1 second I end up getting the requested velocity. And using this method, it allows me to have velocities that are much slower than what I could achieve otherwise. So I could really crawl those motors and have 1 tick per second if I wanted. Alright, so yeah, that is basically what these are doing. Now I'm reading the encoder positions and I'm getting into my PID loop. And here I am shuffling all the proportional errors. So when I'm doing the I term, I need all of my proportional errors from the last, I'm using 8 times. But I need to get rid of the oldest and make space for the newest, and so I'm doing that here. I am calculating the the new error term, and I'm sticking it into that array. Now I'm calculating out my proportional value, which is basically I'm taking what I just stuck into here, the new value, I'm multiplying it by a certain value, and then I'm sticking that into return value. Return val is what's returned by the sign multiply. I'm sticking that into my PID value. Now I'm doing it the same thing with my I term, my integral term. I'm adding up all of the previous errors, including this current one, and I'm once again doing the sign multiply, and I'm adding it in a signed value or signed manner to the PID value. Finally, I'm doing my differential, which is the rate of change of the error. And so I'm basically subtracting the last error from the current one. No, I'm subtracting the current error from the last error. And I'm once again multiplying by the differential term, and I'm adding that in a signed manner into the PID value. Now I'm going to take that and divide it by 16 in a signed manner, because it ends up being too big of a value. And then I am, looks like I'm moving, I forget exactly. I'm setting my PWM values here. I have put in a deadband adjustment so that, let's say I set the velocity to 0 and it comes to a stop, but maybe that motor stopped here and it needs to actually be there. You know, real subtle difference, but the microcontroller is aware of it, and it'll keep doing PWM and making those motors whine and draw current, which is annoying, and it's basically good enough if it's here versus here. So I added in a deadband to prevent that, you know, when there's a low PWM value. And something that I don't have but I would like to do is put in something right now with, I'm using super cheap motors. I think they're $7 a pop, and you kind of get what you pay for when you do that. With a good motor, if I give it 10% PWM, it's going to just start crawling. But with a cheaper motor, you're going to have more of a cogging effect where it sort of wants to be in more preferred positions. And that's happening here. So the motor doesn't actually start turning until I get about to 64 of 256. So it might be something nice to have in the future, though honestly it's working. So I may never get to this. But I put a note in there in case I'm feeling uppity someday and need to fix something. Yeah, so basically that finishes up with one motor, and then I go and do all the same stuff again with the second motor, and that is how I am driving my motors in positionally. And I forget if I said it already or not, but I'm doing the same thing with the accumulator that I did to get my position using velocity. Now I'm using my acceleration to get my velocity. And that's how everything is controlled. And if you enjoyed this video and found it useful, you might take a look at my other videos in this series. And for robotbrigade.com, I'm Jack Buffington.